Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchal and I'm dealing with spectroscopy for chemistry. And in this chapter, this is lecture number 10. And in this lecture, I will explain you the application of Lambert's-Beer's law in ultraviolet spectra. In earlier lecture, I have explained you what is Lambert's-Beer's law. Once again, I'll brief you about these laws. So let us take Lambert's law. When a light is passed through a transparent solid or transparent solution having definite thickness, then certain amount of light is absorbed and certain amount of light will be transmitted. Here B is thickness of solid or path length of light. The unit will be of B will be in centimeter. Then, according to Lambert's law, the amount of light absorbed is directly proportional to the thickness of this material. So, we can have this formula I is equal to I0 e raised to minus kb, where k is proportionality constant, or we write I is equal to I0 10 to the power minus ab, where k is equal to 2.303 A, which is constant. Similarly, Beer's law. This is related to solution. Why? Because here we take concentration, C, of this solution. So here light passes through a transparent solution and some amount of light will be absorbed, some will be transmitted. Beer's law is also related to concentration of solution only, that the amount of light absorbed by the solution is directly proportional to the concentration of solution. Okay, so unit of concentration can be grams per deciliter or moles per liter. So I is equal to I0 e raised to minus k dash c, where k dash is again proportionality constant. So I is equal to I0 10 to the power minus ac, where k dash is equal to 2.303 A. Again it is constant. So here if we combine, or if we see the Lambert's law and Beer's law, they are quite close to each other, and therefore we can combine both these laws. So combining both these equations, we get I is equal to I0 10 to the power minus ABC, or I upon I0 equals to 10 raised to minus ABC. If you want to remove this to the power 10, then we can take log, and negative sign will go here. So minus log I upon I0 is equal to ABC. Okay. If you want to remove negative sign, then we, instead of I upon I0, we can take I0 upon I. So log I0 upon I will be ABC, or log I0 upon I is equal to epsilon BC. Okay. Here either you take A or small a or epsilon, because both are absorptivity. So here A is equal to absorptivity, where concentration will be in grams per deciliter, and epsilon is molar absorptivity, in which case concentration will be in moles per liter. That is the difference between these two. Okay. So let us interpret all these terms in this formula. So interpretation: transmittance, which is related to transmitted light, and symbol is T, is equal to intensity of transmitted light upon intensity of incident light. From this we can have percentage transmittance, which is equal to I upon I0 times 100. So that we get percentage transmittance from transmittance. Okay. Now, as you know that concentration of solution increases, transmittance decreases, and absorption increases. So if we plot percentage transmittance versus concentration, then suppose when sample and reference both contain only pure solvent where there is no solute, that means concentration is 0, the transmittance will be 100%. Why? Because there is 100% pure colorless liquid. It can be water also. So water cannot absorb any light because there is nothing. So 100% transmittance takes place. So this will be the point. If we take colored solution having say 25% concentration, then you may have some amount transmitted, some amount will be absorbed, and therefore transmittance will be less than 100% at this concentration. If you increase concentration, again transmittance will decrease. As absorption increases, transmittance decreases, and this way we get this type of graph for different concentration. As you go from left to right on x-axis, concentration increases, and here transmittance decreases. So finally graph will be like this. Okay. It is non-linear graph, which is not useful to find out concentration, unknown concentration of a solution. Why? Because it may not be fall on this line. That is why it is necessary to take different kind of graph. This is not useful in fact. So let us see what we can do with this. As we know, transmittance is equal to I upon I0. Okay. Opposite of transmittance theoretically would be absorbance. Because if transmittance increases, absorbance decreases, vice versa. A. So, and the formula is A is equal to log I0 upon I. And you know log I0 upon I is equal to ABC, or epsilon BC, okay, where B is thickness or path length and C is concentration. So we can write absorbance A is equal to ABC, absorptivity into thickness or path length into concentration, or epsilon BC, okay, where B is path length of light or length of cuvette in which we filled solution and through which light is passing. Therefore, this length is set because we decide this. This length is set. And taken as 1 centimeter, 2 centimeter, etc. But it is fixed. Such, therefore, we can say B is constant. It is not variable. Epsilon, that is known as molar absorptivity, or molar extinction coefficient. It is also set, and it is set by chemical compound and a wavelength at which it is absorbed. Therefore, epsilon is also a constant. Okay, so in this formula, A is equal to epsilon BC, epsilon and B are constant. Now, when we have to plot a graph of A versus concentration, remember A versus concentration C, okay, then we have to compare this with Y is equal to mx plus C. Here C means interception, and there is nothing plus this, it is 0. That means for this graph of A versus C, there is no interception, okay. That means if A versus C is plotted, the line will pass through origin. With zero interception. Okay. Therefore, the graph will be like this. Here, this is absorbance versus concentration C, and the mode of graph would be like this.